Here is an example of using the parallel axis theorem to find the second moment of area for a composite area. The first step is to find the centroid. Because of the symmetry to the left and right of the y-axis, the x-coordinate of the centroid is at the center. But we need to break this area up to find the y-centroid. Here is a natural way to break up the area into two rectangles. We will find the centroids and areas of the two rectangles and then combine them. Here is the table we will use to record the results. Start with the area that we labeled 1. It is 2 by 6 or 12 square millimeters. Here is its centroid. Notice its y position relative to the baseline horizontal axis at the bottom. So we record 5 millimeters as the y position of the centroid of area 1. And then find the product of centroid position and area. Now let's move on to area 2. Its area is 4 by 2 or 8 square millimeters. Here is its centroid. So the position of its centroid relative to the bottom is 1 millimeter. And here is the product of the centroid position and area for area 1. Here, both individual centroids are shown in the drawing. Here is the total area, which we find by summing the areas. Sum the products of centroid position and area. Apply the general formula to this combination of two areas, and we find the centroid of the whole figure to be 3.4 millimeters from the bottom. You did this procedure before in an earlier module. We are now going to find the second moment of area about the x-axis through the centroid that we just found. We add the second moment of area 1 with that of area 2. Start with area 1. Here it is, and here is the centroid of just area 1. We want the second moment of area about the centroid of the whole figure, but area 1 has a centroid at a different point. We can use the parallel axis theorem. First we find the second moment of area 1 about its own centroid. As a rectangle, its second moment of area is base times height cubed over 12. Here we show the distance between the centroid of area 1 and the centroid of the whole figure. And we enter that distance into the table as d sub y of part 1. We find the additional contribution to the second moment of area 1 by computing the distance dy of area 1 squared times the area of 1. And now we add the two contributions to find the total second moment of area 1 about the centroid of the whole figure. Now we apply the same procedure to area 2. For area 2, which is a rectangle, the second moment of area about its own centroid is again base times height cubed over 12. Here is the distance we need between the centroid of area 2 and the centroid of the whole figure. The distance d sub y for area 2 is entered into the table. We find the additional contribution to the second moment of area 2 by computing the distance dy of area 2 squared times the area of 2. And now we add the two contributions to find the total second moment of area 2 about the centroid of the whole figure. We now add the second moments of area for the two areas, each of them about the centroid of the whole figure, to find the total second moment of area. Notice that this is the second moment of area I sub x about the x-axis through the centroid. Finding the second moment of area IY about the y-axis through the centroid is simpler. The x-coordinate of the centroid of the figure coincides with the x-coordinate of the centroids of the individual areas. There is no need to use the parallel axis theorem. We find the second moment of area IY for area 1 and add it to the second moment of area IY for area 2.